Imagine a star so dense that a single teaspoon of its material would weigh as much as a mountain. Now, picture that same star spinning hundreds of times per second, emitting beams of radiation so powerful they can be detected across the galaxy. This isn't science fiction, it's the reality of neutron stars, some of the most bizarre and mysterious objects in the universe. These cosmic enigmas challenge everything we think we know about physics, bending the rules of space, time, and matter in ways that leave even the brightest scientists in awe. Today, we're diving into 25 specific space mysteries surrounding the strange behavior of neutron stars. From their mind-bending formation to their explosive deaths, these celestial wonders hold secrets that could reshape our understanding of the cosmos. So, buckle up and get ready to explore the extremes of the universe, where the ordinary becomes extraordinary and the impossible becomes reality. By the end of this video, you'll not only grasp the incredible nature of neutron stars, but also uncover why they're key to unlocking some of the universe's greatest mysteries. Let's begin this journey into the unknown. Now, let's take a closer look at how these incredible objects come into existence. Neutron stars are born from the dramatic and violent deaths of massive stars in events known as supernova explosions. When a star many times more massive than our Sun exhausts its nuclear fuel, it can no longer support its own weight. The core collapses under its own gravity, triggering a cataclysmic explosion that blasts the outer layers of the star into space. What remains is an incredibly dense core, compressed to the point where protons and electrons are forced together to form neutrons. This is the birth of a neutron star. To put their density into perspective, imagine taking a sugar cube-sized piece of a neutron star. That tiny cube would weigh as much as a mountain here on Earth. Despite being only about 12 miles across, neutron stars pack the mass of 1.4 times our Sun into that small space. This extreme density is what makes them so fascinating and so challenging to study. The conditions inside a neutron star are unlike anything we can recreate on Earth, pushing the boundaries of our understanding of physics. From their explosive beginnings to their mind-boggling density, neutron stars are a testament to the incredible forces at work in the universe. And this is just the start of their story. Next, we'll explore how these dense remnants of stellar explosions become cosmic lighthouses, emitting beams of radiation that sweep across the galaxy. Now, shifting our focus to one of the most mesmerizing behaviors of neutron stars, let's dive into the world of pulsars. These are neutron stars that emit beams of radiation, and they do so in a way that makes them some of the most fascinating objects in the cosmos. Picture this: as a pulsar spins, it sends out narrow beams of light and other forms of radiation from its magnetic poles. These beams sweep across space like the light from a cosmic lighthouse, creating what astronomers call the lighthouse effect. But here's the intriguing part: when these beams happen to point toward Earth, we detect them as regular pulses of radiation. This is why they're called pulsars, short for pulsating stars. The pulses can be incredibly precise, with some pulsars spinning hundreds of times per second, making them some of the most accurate natural clocks in the universe. Imagine a star spinning so fast that it completes a full rotation in just a few milliseconds. That's the kind of speed we're talking about. What's even more remarkable is that the timing of these pulses can tell us a lot about the pulsar itself. By studying the intervals between pulses, scientists can measure the pulsar's rotation speed, its magnetic field strength, and even its movement through space. This precision has made pulsars invaluable tools for testing theories of gravity and exploring the fabric of space-time. So, why do these beams appear to pulse from our perspective? It all comes down to the alignment of the pulsar's magnetic poles and its axis of rotation. If the beams aren't perfectly aligned with the rotation axis, they sweep across the sky in a circular pattern. When one of these beams crosses Earth, we see a flash of light. As the pulsar continues to spin, the beam moves away and the light disappears until the next rotation brings it back into view. This rhythmic on and off pattern is what gives pulsars their signature pulse. Pulsars are not just cosmic curiosities, they're windows into the extreme physics of neutron stars. From their rapid spins to their precise pulses, these stellar remnants continue to challenge our understanding of the universe. And as we'll see next, some neutron stars take this extreme behavior to an even higher level, with magnetic fields so powerful they defy imagination. Now let's turn our attention to something even more extreme than pulsars' magnetars. These are a special kind of neutron star, but with a twist that makes them truly extraordinary. Imagine a neutron star, already one of the densest objects in the universe, but now give it a magnetic field so powerful it defies comprehension. We're talking about magnetic fields trillions of times stronger than Earth. To put that into perspective, if a magnetar were halfway between the Earth and the Moon, it could strip the information off every credit card on our planet. That's the kind of power we're dealing with. So, what makes magnetars so magnetic? It all comes down to their formation. When a massive star collapses into a neutron star, its magnetic field gets compressed and amplified to unimaginable levels. This creates a magnetar, a neutron star with a magnetic field so intense it can warp the very fabric of space around it. But these magnetic fields aren't just for show. They have real, dramatic effects on the magnetar itself and its surroundings. One of the most striking consequences of these intense magnetic fields is something called a starquake. Just like earthquakes on Earth, starquakes are sudden shifts or cracks in the magnetar's crust. But unlike earthquakes, these shifts are driven by the immense stress of the magnetic field twisting and pulling on the star's surface. When a starquake happens, it releases an enormous burst of energy, often in the form of X-rays or gamma rays. These bursts can be so powerful that they're detectable across the galaxy, even from thousands of light years away. But that's not all. Magnetars are also thought to be the source of some of the most mysterious signals in the universe: fast radio bursts. These are incredibly brief but intense flashes of radio waves that last just milliseconds. While the exact cause of fast radio bursts is still a mystery, magnetars are one of the leading suspects. Their powerful magnetic fields and energetic outbursts make them prime candidates for producing these enigmatic signals. What's truly fascinating is that magnetars don't just sit quietly in space. They're dynamic, unpredictable, and capable of releasing more energy in a fraction of a second than our Sun does in years. This makes them some of the most violent and energetic objects in the cosmos. Yet, despite their ferocity, magnetars are also incredibly rare. Scientists estimate that only about 1 in 10 neutron stars becomes a magnetar, making them a precious window into the extremes of physics. As we continue to study these magnetic powerhouses, we're not just learning about magnetars, we're uncovering clues about the fundamental forces that shape our universe. And as we'll see next, neutron stars have even more surprises in store, from their rapid spins to the mysterious signals they send across the cosmos. Now, let's dive into one of the most puzzling phenomena in the cosmos: fast radio bursts, or FRB. These are incredibly brief but intense flashes of radio waves that last just milliseconds, yet they pack enough energy to outshine entire galaxies for that fleeting moment. What makes them even more intriguing is that they seem to come from deep space, often billions of light years away. But what could possibly produce such a sudden and powerful burst of energy? The answer might lie in the very objects we've just been discussing: neutron stars, and more specifically, magnetars. Magnetars, with their unimaginably strong magnetic fields, are prime suspects in the mystery of fast radio bursts. Their magnetic fields are so intense that they can twist and snap, releasing enormous amounts of energy in the process. This energy can manifest as bursts of radiation, including X-rays, gamma rays, and potentially radio waves. Scientists believe that when a magnetar experiences a starquake or a sudden rearrangement of its magnetic field, it could produce a fast radio burst. These events are so powerful that they can send ripples of energy across the universe, detectable even from billions of light years away. But magnetars aren't the only possible explanation. Some theories suggest that fast radio bursts could also come from collisions between neutron stars, or even from the interaction of neutron stars with black holes. Others propose that they might be caused by highly energetic processes in the early universe, such as the collapse of massive stars or the evaporation of primordial black holes. However, magnetars remain one of the most compelling candidates, especially since we've observed a few FRBs originating from regions of space where magnetars are known to exist. One of the most exciting developments in this field came in 2020, when astronomers detected a fast radio burst coming from a magnetar within our own galaxy. This was a game changer because it provided the first direct evidence linking magnetars to FRBs. The burst was accompanied by X-ray emissions, further supporting the idea that these magnetic powerhouses could be the source of these mysterious signals. Yet, even with this discovery, many questions remain. Why do some magnetars produce FRBs while others don't? What exactly triggers these bursts, and are there other sources out there that we haven't yet identified? The study of fast radio bursts is still in its early stages, but every new detection brings us closer to unraveling their secrets. These bursts are like cosmic breadcrumbs, leading us to some of the most extreme and energetic events in the universe. And as we continue to explore, we're not just solving the mystery of FRBs, we're gaining deeper insights into the behavior of neutron stars, the nature of magnetic fields, and the fundamental forces that govern our universe. As we move forward, we'll explore another fascinating aspect of neutron stars, their incredible speed of rotation. Just how fast can these cosmic powerhouses spin, and what does that tell us about their inner workings? Stay tuned because the surprises don't stop here. Now, let's shift our focus to one of the most jaw-dropping features of neutron stars, their mind-blowing speed of rotation. Imagine an object so dense that a teaspoon of its material would weigh as much as a mountain, yet it spins faster than a kitchen blender. Some neutron stars rotate hundreds of times every single second. To put that into perspective, if Earth spun that fast, a day would last less than a fraction of a second. But how do these cosmic powerhouses achieve such incredible speeds? The answer lies in the conservation of angular momentum. When a massive star collapses into a neutron star, it shrinks dramatically, but its spin speeds up to conserve the total angular momentum. Think of it like a figure skater pulling in their arms during a spin. They rotate faster as they become more compact. In the case of neutron stars, this effect is taken to the extreme. The original star might have taken weeks or even months to complete a single rotation, but after collapsing into a neutron star, it can spin hundreds of times per second. This rapid rotation isn't just a cosmic curiosity, it's a window into the internal structure of neutron stars. The way they spin can reveal details about their density, composition, and even the exotic states of matter that might exist inside them. For instance, if a neutron star's rotation slows down over time, it could indicate that energy is being lost through processes like magnetic braking or the emission of gravitational waves. On the other hand, sudden changes in rotation, known as glitches, might point to starquakes or shifts in the star's interior. One of the fastest spinning neutron stars ever discovered is known as a millisecond pulsar. These objects can complete a full rotation in just a few milliseconds, making them some of the most precise cosmic clocks in the universe. Their incredible stability allows scientists to use them to test theories of gravity and even detect gravitational waves. But even these speed demons have their limits. If a neutron star spins too fast, it could tear itself apart as the centrifugal force overcomes the immense gravitational pull holding it together. The study of neutron star rotation isn't just about understanding these extreme objects, it's also about uncovering the fundamental laws of physics that govern our universe. By observing how neutron stars spin, we can test theories about the behavior of matter under conditions that are impossible to recreate on Earth. And as we continue to explore, we're not just learning about neutron stars, we're gaining insights into the very fabric of space and time. Next, we'll take a closer look at the outer layer of a neutron star, the crust. What secrets does this solid surface hold, and how does it behave under the crushing pressure of the star's immense gravity? Stay with us as we uncover more about these cosmic enigmas. Now, let's peel back the layers literally and explore the outer shell of a neutron star known as the crust. This solid surface, though only a few kilometers thick, is one of the most fascinating and extreme environments in the universe. Picture a material so dense that a single sugar cube-sized piece would weigh billions of tons. Yet, despite this unimaginable density, the crust is solid, forming a rigid outer layer that encases the star's exotic interior. The crust of a neutron star is under immense pressure, billions of times stronger than anything we experience on Earth. This pressure is so extreme that it forces atomic nuclei into a lattice-like structure, creating a crystalline surface. But don't let the word crystalline fool you. This isn't like any crystal you've seen before. The nuclei are packed so tightly that electrons are squeezed out, forming a sea of free electrons that flow through the lattice. This unique arrangement gives the crust its incredible strength and stability, even under the crushing weight of the star's gravity. But the crust isn't perfectly smooth. Scientists believe that neutron stars might have mountains on their surfaces, tiny deformations caused by the immense forces at play. These mountains, however, are nothing like the peaks we see on Earth. They're only a few centimeters high, but because of the neutron star's extreme density, even these small bumps can weigh as much as entire mountain ranges on our planet. These imperfections might seem insignificant, but they play a crucial role in the star's behavior. One of the most intriguing effects of these surface mountains is their impact on gravitational waves. When a neutron star rotates, these tiny deformations create ripples in spacetime, sending out gravitational waves that can be detected by observatories like LIGO. The size and shape of these mountains determine the strength and frequency of the waves, providing scientists with valuable clues about the star's structure and rotation. In fact, studying these gravitational waves could help us map the surface of a neutron star in unprecedented detail, revealing secrets about its crust and interior. The crust also plays a key role in another mysterious phenomenon, starquakes. Just like earthquakes on Earth, starquakes occur when the crust undergoes sudden shifts or fractures, releasing massive amounts of energy. These events can cause the star's rotation to speed up or slow down, creating the glitches we've observed in some pulsars. By studying these quakes, scientists hope to learn more about the crust's composition and how it interacts with the star's interior. As we continue to explore the crust of neutron stars, we're not just uncovering the secrets of these cosmic objects, we're also gaining insights into the fundamental nature of matter under extreme conditions. The crust is a window into a world where the rules of physics are pushed to their limits, and every discovery brings us closer to understanding the universe's most enigmatic phenomena. Next, we'll venture even deeper into the mysterious interior of a neutron star. What lies beneath the crust, and how do the strange states of matter inside these stars challenge our understanding of physics? Stay tuned as we dive into the heart of these cosmic wonders. Now, let's journey into the heart of a neutron star where the mysteries only deepen. Beneath the crust lies an interior so extreme and bizarre that it challenges everything we know about matter and physics. Imagine a place where the rules of the universe as we understand them are rewritten, where matter exists in states so strange they seem almost otherworldly. This is the interior of a neutron star, a realm of superfluid neutrons, exotic particles, and perhaps even quark matter. At the core of a neutron star, the pressure is unimaginable, far greater than even the crushing forces found in the crust. Here, neutrons, the building blocks of atomic nuclei, are no longer confined within atoms. Instead, they flow freely, forming what scientists call a neutron superfluid. This superfluid behaves unlike any liquid we know on Earth. It has no friction, meaning it can flow endlessly without losing energy. This frictionless state is thought to play a key role in the star's rotation, helping to explain why some neutron stars spin hundreds of times per second without slowing down. But the interior doesn't stop at superfluid neutrons. As we go deeper, the conditions become even more extreme, and the nature of matter itself begins to change. Some theories suggest that the intense pressure and density might break down neutrons into their constituent particles, quarks. Quarks are the fundamental particles that make up protons and neutrons, and under normal conditions, they're never found alone. But inside a neutron star, the rules are anything but normal. Here, quarks might exist in a free state, forming what's known as quark matter. This exotic substance could be the densest form of matter in the universe, even more so than the neutrons themselves. The idea of quark matter opens up a world of possibilities. Some scientists speculate that the core of a neutron star might contain a quark-gluon plasma, a state of matter that hasn't existed since the earliest moments of the universe, just after the Big Bang. This plasma would be a soup of quarks and gluons, the particles that hold quarks together, moving freely without forming protons or neutrons. If this theory is correct, neutron stars could be cosmic time capsules, preserving conditions that haven't existed anywhere else for billions of years. Another intriguing possibility is the existence of strange matter, a hypothetical form of quark matter that includes strange quarks, a heavier and more exotic type of quark. Strange matter is thought to be incredibly stable, potentially even more stable than the matter we're familiar with. If it exists inside neutron stars, it could mean that these stars are not just made of neutrons but are instead strange stars, composed entirely of this bizarre substance. The implications of this are profound, as it could change our understanding of the fundamental nature of matter itself. Yet, despite these fascinating theories, the interior of a neutron star remains one of the greatest unsolved mysteries in astrophysics. The extreme conditions make it impossible to recreate in laboratories, and our observations are limited to indirect clues such as gravitational waves and X-ray emissions. Every new discovery, however, brings us closer to unraveling the secrets of these cosmic enigmas. As we continue to explore the interior of neutron stars, we're not just learning about these distant objects, we're pushing the boundaries of our understanding of the universe itself. What lies at the core of a neutron star? Is it a sea of superfluid neutrons, a quark-gluon plasma, or something even stranger? The answers could redefine our knowledge of physics and the very fabric of reality. Next, we'll turn our attention to the dramatic collisions of neutron stars and the incredible gravitational waves they produce. What happens when two of these cosmic powerhouses collide, and what can these events teach us about the universe? Stay with us as we explore the explosive aftermath of neutron star mergers. Now, let's shift our focus to one of the most dramatic events in the cosmos, the collision of neutron stars. When two of these incredibly dense objects spiral toward each other and finally collide, the result is nothing short of spectacular. These collisions don't just create a burst of light and energy, they send ripples through the very fabric of space-time itself, known as gravitational waves. Gravitational waves are disturbances in space-time caused by massive objects accelerating, like two neutron stars orbiting each other at incredible speeds. As these stars get closer, their immense gravity pulls them together faster and faster until they finally merge in a cataclysmic explosion. This merger sends out powerful gravitational waves that travel across the universe at the speed of light, carrying with them information about the event that created them. In 2017, scientists made history when they detected gravitational waves from a neutron star collision for the first time. This groundbreaking discovery was made by the Laser Interferometer Gravitational Wave Observatory, or LIGO, along with its European counterpart, Virgo. The detection wasn't just a triumph of technology, it was a milestone in astrophysics. For the first time, we not only heard the collision through gravitational waves, but also saw it in the form of light, thanks to telescopes observing the event across multiple wavelengths. The collision produced a phenomenon known as a kilonova, an explosion so powerful that it outshines entire galaxies for a brief moment. But the significance of this event goes far beyond its brightness. The merger of neutron stars is thought to be a cosmic factory for heavy elements like gold, platinum, and uranium. The intense conditions during the collision create the perfect environment for these elements to form, scattering them into space where they can eventually become part of new stars, planets, and even life. The detection of gravitational waves from neutron star collisions has opened up a new way of observing the universe. Before this, our understanding of the cosmos relied almost entirely on light, visible light, X-rays, radio waves, and so on. But gravitational waves give us a completely different perspective, allowing us to listen to the universe in a way we never could before. This has led to a new field of science called multi-messenger astronomy, where gravitational waves and light are used together to paint a fuller picture of cosmic events. These discoveries have also provided crucial tests for Einstein's theory of general relativity. Gravitational waves were predicted by Einstein over 100 years ago, but it wasn't until recently that we had the technology to detect them. The observations from neutron star collisions have confirmed Einstein's predictions with remarkable precision, while also raising new questions about the nature of gravity and the behavior of matter under extreme conditions. As we continue to detect more neutron star collisions, each event brings new insights. They help us understand how these stars form, how they evolve, and how they contribute to the chemical makeup of the universe. They also give us a glimpse into the fundamental forces that shape our cosmos. The collision of neutron stars is not just a spectacular cosmic event, it's a window into the very heart of the universe itself. Next, we'll explore how these neutron star mergers play a crucial role in creating the heavy elements that make up our world. How do these cosmic collisions forge the building blocks of planets and even life? Stay with us as we uncover the secrets of neutron stars and their role in the cosmic cycle of creation. Now, let's dive into one of the most fascinating aspects of neutron star collisions, their role in creating the heavy elements that make up our universe. When two neutron stars collide, the sheer energy and extreme conditions of the merger create a cosmic forge unlike anything else in nature. This process, known as nucleosynthesis, is responsible for producing some of the heaviest elements in the periodic table, including gold, platinum, and uranium. During a neutron star collision, the intense pressure and temperature cause neutrons to bombard atomic nuclei at incredible speeds. This rapid capture of neutrons, called the R process, allows lighter elements to transform into heavier ones in a matter of seconds. The R process is so efficient that it can produce elements far heavier than those formed in the cores of stars or during supernova explosions. As the collision unfolds, these newly formed heavy elements are ejected into space, scattering across the cosmos like cosmic seeds. The discovery of heavy elements in the aftermath of neutron star mergers has been a game-changer for astrophysics. Before this, scientists believed that supernovae were the primary source of these elements. But the detection of gold and platinum in the light emitted from kilonovae, the explosive aftermath of neutron star collisions, has shifted our understanding. These mergers are now thought to be one of the main contributors to the abundance of heavy elements in the universe. This has profound implications for our own existence. The gold in your jewelry, the platinum in catalytic converters, and even the uranium used in nuclear reactors were likely forged in the fiery crucibles of neutron star collisions billions of years ago. These elements were scattered into space, eventually becoming part of the gas clouds that formed new stars, planets, and ultimately life itself. In a very real sense, we are made of stardust, but some of that stardust was born in the violent collisions of neutron stars. The study of neutron star mergers and their role in creating heavy elements is still in its early stages, but each new discovery brings us closer to understanding the cosmic origins of the materials that shape our world. As we continue to observe these spectacular events, we gain not only a deeper appreciation for the universe's complexity, but also a clearer picture of our own place within it. Next, we'll turn our attention to another intriguing mystery, the sudden speed-ups in neutron star rotation, known as glitches. What causes these strange events, and what can they tell us about the inner workings of these cosmic powerhouses? Stay tuned as we unravel the secrets of pulsar glitches. Now, let's shift our focus to one of the most puzzling behaviors of neutron stars, the sudden and unexpected speed-ups in their rotation, known as pulsar glitches. Imagine a cosmic clock ticking with incredible precision, only to suddenly jump forward without warning. That's exactly what happens when a pulsar glitches. These strange events have baffled scientists for decades, and they offer a unique window into the inner workings of these dense stellar remnants. Pulsar glitches occur when a neutron star's rotation abruptly increases in speed, sometimes by a tiny fraction of a second, but occasionally by a more noticeable amount. This sudden change is like a skater pulling their arms in mid-spin, causing them to spin faster. But what causes this cosmic speed up? One leading theory points to starquakes, massive shifts in the neutron star's crust. Just as earthquakes reshape Earth's surface, starquakes can cause the outer layers of a neutron star to crack and shift, altering its rotation. Another possibility lies deep within the neutron star's interior. Some scientists believe that glitches are caused by changes in the superfluid core, a bizarre state of matter where particles flow without friction. In this scenario, the superfluid core might suddenly transfer angular momentum to the star's crust, causing it to spin faster. Think of it like a pot of water on a stove. As the water heats up, it begins to swirl, and if the swirling becomes intense enough, it can jolt the pot. Similarly, the superfluid core's behavior could be the hidden force behind these glitches. Despite decades of research, pulsar glitches remain a mystery. Each glitch provides a new piece of the puzzle, but the full picture is still unclear. What we do know is that these events are not random. They seem to follow patterns, with some pulsars glitching more frequently than others. By studying these patterns, scientists hope to uncover the underlying mechanisms driving these cosmic hiccups. Pulsar glitches are more than just a curiosity. They're a key to understanding the extreme physics of neutron stars. By unraveling the secrets behind these sudden speed-ups, we gain insight into the behavior of matter under conditions that are impossible to replicate on Earth. As we continue to observe and analyze these glitches, we move closer to solving one of the many mysteries that make neutron stars such fascinating objects in the cosmos. Next, we'll explore another intriguing aspect of neutron stars, how they cool over time and the mysteries surrounding their cooling rates. What happens to these stellar remnants as they lose heat, and what can their cooling tell us about their interiors? Stay tuned as we dive into the strange and fascinating process of neutron star cooling. Now, let's turn our attention to another fascinating mystery of neutron stars, how they cool over time. Picture a star that has burned brightly for millions of years, only to collapse into a dense, city-sized remnant. But even after this dramatic transformation, the story isn't over. Neutron stars continue to lose heat, and the way they cool holds clues to their inner workings and the exotic physics at play. When a neutron star is born from a supernova explosion, it's incredibly hot, reaching temperatures of billions of degrees. Over time, however, it begins to cool, but this cooling process isn't as straightforward as you might think. Unlike a cup of coffee left on a table, neutron stars don't cool at a steady rate. Instead, their cooling is influenced by a complex interplay of factors, including their composition, magnetic fields, and the particles they emit. One of the key players in this cooling process is the neutrino, a ghostly particle that barely interacts with matter. Neutron stars produce vast numbers of neutrinos, especially in their early stages, and these particles carry away a significant amount of heat. Imagine a radiator releasing steam into the air. Neutrinos act in a similar way, escaping the star and taking energy with them. This neutrino-driven cooling is one of the primary ways neutron stars lose heat in their first million years. But as neutron stars age, their cooling slows down. This is where things get even more intriguing. Scientists have observed that some neutron stars cool faster than expected, while others seem to hold onto their heat longer. What's causing these differences? One theory points to the presence of exotic particles or states of matter in the star's core. For instance, if the core contains superfluid neutrons or even stranger forms of matter like quark-gluon plasma, these could affect how heat is transported and lost. Another factor is the star's magnetic field. Neutron stars with strong magnetic fields might cool differently than those with weaker fields. The magnetic field can influence how particles move within the star, potentially trapping heat or altering the flow of energy. It's like how a blanket can keep you warm by trapping heat close to your body, except in this case, the blanket is a magnetic field billions of times stronger than Earth. Despite decades of research, the cooling rates of neutron stars remain a puzzle. Each star seems to follow its own unique cooling curve, and scientists are still working to understand why. By studying these cooling patterns, we can learn more about the extreme conditions inside neutron stars and the behavior of matter under pressures and temperatures that are impossible to recreate on Earth. The cooling of neutron stars isn't just a cosmic curiosity, it's a window into the physics of the universe's most extreme environments. As we continue to observe and analyze these stellar remnants, we move closer to unraveling the mysteries of their interiors and the strange particles that call them home. Next, we'll explore another enigmatic aspect of neutron stars, their X-ray emissions and what these powerful bursts of energy reveal about their magnetic fields and interactions with the surrounding space. Stay tuned as we dive into the high-energy world of neutron star X-rays. Now, let's shift our focus to the high-energy world of neutron stars and their X-ray emissions. These powerful bursts of energy are more than just flashes in the cosmos. They're a key to unlocking the secrets of neutron stars' magnetic fields, temperatures, and their interactions with the space around them. When we think of X-rays, we often picture medical imaging or airport security scanners. But in the realm of neutron stars, X-rays are a natural byproduct of their extreme environments. Neutron stars emit X-rays for a variety of reasons, and each type of emission tells us something unique about the star's behavior. For instance, some X-rays come from the star's surface, where temperatures can reach millions of degrees. These emissions give us a glimpse into the star's thermal state, helping scientists estimate how hot the surface is and how it changes over time. But surface emissions are just the beginning. Neutron stars also produce X-rays through their intense magnetic fields. As charged particles spiral along these magnetic field lines, they emit X-rays in a process known as synchrotron radiation. This phenomenon is especially prominent in pulsars, where the magnetic field is so strong that it accelerates particles to nearly the speed of light. The result, bright, focused beams of X-rays that sweep across the cosmos like a lighthouse, detectable from thousands of light years away. Another fascinating source of X-rays is the interaction between neutron stars and their surroundings. Many neutron stars exist in binary systems where they orbit another star. In these systems, the neutron star's gravity can pull material from its companion, creating a swirling disk of gas and dust around it. As this material spirals inward, it heats up to extreme temperatures, emitting X-rays in the process. These X-rays not only reveal the presence of the accretion disk, but also provide clues about the rate at which the neutron star is consuming material. Sometimes neutron stars produce sudden, intense bursts of X-rays known as X-ray bursts. These events occur when accumulated material on the star's surface undergoes a runaway nuclear reaction, releasing a massive amount of energy in a matter of seconds. By studying these bursts, scientists can learn about the composition of the material being accreted and the conditions on the neutron star's surface. The study of X-ray emissions from neutron stars has revolutionized our understanding of these cosmic powerhouses. By analyzing the energy, timing, and patterns of these X-rays, researchers can map the structure of magnetic fields, measure surface temperatures, and even infer the presence of exotic particles or states of matter within the star. Each X-ray photon carries a piece of the puzzle, helping us piece together the story of neutron stars and their role in the universe. As we continue to explore the mysteries of neutron stars, their X-ray emissions remain one of the most valuable tools in our cosmic toolkit. Next, we'll delve into another intriguing aspect of these stellar remnants, their thin atmospheres and the challenges of studying them. Stay tuned as we uncover more about the outer layers of neutron stars and what they reveal about these enigmatic objects. Now, let's turn our attention to the outermost layer of neutron stars, their atmospheres. These thin, delicate layers are incredibly challenging to study, yet they hold vital clues about the composition and behavior of these cosmic giants. Unlike the thick, gaseous atmospheres of planets or stars, neutron star atmospheres are incredibly sparse, often just a few centimeters thick. This makes them one of the most elusive features to observe and understand in the universe. The primary challenge in studying neutron star atmospheres lies in their extreme conditions. The intense gravity of a neutron star compresses its atmosphere to such an extent that it behaves unlike anything we're familiar with on Earth. The pressure and density are so high that atoms are crushed and electrons are stripped away, leaving behind a plasma of ions and free electrons. This unique state of matter makes it difficult to apply traditional atmospheric models, forcing scientists to develop entirely new frameworks to interpret their observations. One of the key tools in unraveling the mystery of neutron star atmospheres is spectroscopy. By analyzing the light emitted or absorbed by these atmospheres, scientists can identify the elements present and their physical conditions. For example, when X-rays pass through a neutron star's atmosphere, certain wavelengths are absorbed by specific elements, creating a unique fingerprint in the spectrum. This allows researchers to determine the chemical composition of the atmosphere, even from thousands of light years away. However, spectroscopy isn't without its challenges. The extreme magnetic fields of neutron stars can distort the spectral lines, making them harder to interpret. Additionally, the intense gravitational field bends light in a phenomenon known as gravitational lensing, further complicating the analysis. Despite these obstacles, advancements in telescope technology and computational models have allowed scientists to make significant progress in decoding these spectral signatures. One of the most intriguing discoveries from these studies is the presence of heavy elements like iron and carbon in neutron star atmospheres. These elements are thought to be remnants of the supernova explosion that created the neutron star, or they may have been accreted from a companion star in a binary system. Understanding their abundance and distribution helps scientists piece together the history and evolution of neutron stars. Another fascinating aspect of neutron star atmospheres is their role in shaping the star's observable properties. The atmosphere acts as a filter, absorbing and re-emitting radiation in ways that can dramatically alter the star's appearance. For instance, the atmosphere can make a neutron star appear brighter or dimmer depending on its composition and temperature. This variability provides valuable insights into the star's internal structure and the processes occurring beneath its surface. As we continue to explore the mysteries of neutron star atmospheres, each discovery brings us closer to understanding these enigmatic objects. Next, we'll dive into the complex relationships between neutron stars and their companion stars, uncovering how these cosmic partnerships influence their behavior and evolution. Stay tuned as we explore the dynamic interactions that shape the lives of neutron stars. Now, let's shift our focus to the fascinating relationships neutron stars share with their companion stars. These cosmic partnerships are not just about gravitational attraction, they're dynamic, evolving systems that reveal some of the most intriguing behaviors in the universe. Neutron stars often exist in binary systems where they orbit another star, and these interactions can lead to extraordinary phenomena that challenge our understanding of astrophysics. One of the most significant ways neutron stars interact with their companions is through gravitational forces. The immense gravity of a neutron star can distort the shape of its companion, pulling material from its outer layers. This process, known as mass transfer, creates a flow of gas and dust from the companion star to the neutron star. As this material spirals inward, it forms an accretion disk around the neutron star, heating up and emitting intense radiation, often in the form of X-rays. These X-ray emissions are a key way scientists detect and study these binary systems, but the story doesn't end there. The material being transferred isn't just passive, it can dramatically alter the neutron star's behavior. For instance, if the neutron star is a pulsar, the influx of material can cause its rotation to speed up, a phenomenon known as recycling. This process can turn an old, slow-spinning pulsar into a millisecond pulsar, spinning hundreds of times per second. It's a cosmic makeover driven by the relentless pull of gravity and the flow of matter between stars. In some cases, the relationship between a neutron star and its companion can become explosive. If the companion star is a white dwarf or another neutron star, the system can eventually merge, releasing an enormous amount of energy in the form of gravitational waves and light. These mergers are not only spectacular events, but also crucial for understanding how heavy elements like gold and platinum are formed in the universe. The collision of two neutron stars is thought to be one of the primary sources of these rare elements, scattering them across space where they can eventually become part of new stars and planets. However, not all neutron star companions are stars. Some neutron stars are paired with planets, though these systems are incredibly rare. The intense radiation and gravitational forces from the neutron star make it a hostile environment for any orbiting planets, often stripping away their atmospheres or even tearing them apart. Yet the discovery of such systems challenges our assumptions about where and how planets can exist, pushing the boundaries of what we thought was possible. The interactions between neutron stars and their companions are a testament to the complexity and diversity of the cosmos. Each system tells a unique story, offering insights into the life cycles of stars, the formation of elements, and the extreme conditions that shape the universe. As we continue to study these relationships, we uncover new layers of mystery and wonder, reminding us just how much there is still to learn. Next, we'll explore another captivating aspect of neutron stars, their powerful jets of particles and radiation. These jets are some of the most energetic phenomena in the universe, and understanding them could unlock even more secrets about these enigmatic objects. Stay tuned as we dive into the mystery of neutron star jets. Now, let's turn our attention to one of the most dramatic displays of cosmic power, neutron star jets. These jets are not just spectacular to observe, they are also key to understanding some of the most extreme processes in the universe. When a neutron star produces jets, it sends out narrow beams of particles and radiation at nearly the speed of light, creating some of the most energetic phenomena we know of. But what exactly causes these jets to form? The answer lies in the intense magnetic fields and rapid rotation of neutron stars. When a neutron star is part of a binary system, material from its companion star can flow onto the neutron star, forming an accretion disk. As this material spirals inward, it gets heated to incredible temperatures, releasing vast amounts of energy. In some cases, this energy is channeled into powerful jets that shoot out from the poles of the neutron star. These jets are often aligned with the star's magnetic axis, which can be tilted relative to its rotational axis, creating a stunning cosmic lighthouse effect. The conditions required for jet formation are extreme. The neutron star must have a strong magnetic field, typically trillions of times stronger than Earth's, and it must be spinning rapidly. The interaction between the magnetic field and the accretion disk plays a crucial role in launching these jets. As material in the disk interacts with the magnetic field, it gets funneled along the field lines and ejected outward in two opposing directions. This process is so efficient that it can convert a significant fraction of the infalling material's energy into the kinetic energy of the jets. The impact of these jets on the surrounding space is profound. As they travel outward, they can collide with interstellar gas and dust, creating shock waves that heat the surrounding material and emit radiation across the electromagnetic spectrum. These interactions can even trigger the formation of new stars by compressing nearby gas clouds. In some cases, the jets extend for thousands of light years, leaving behind vast structures known as radio lobes, which can be observed by telescopes. One of the most fascinating aspects of neutron star jets is their variability. The intensity and direction of the jets can change over time, depending on the rate of material flowing onto the neutron star and the stability of the accretion disk. This variability provides scientists with valuable clues about the dynamics of these systems and the physical processes at work. Studying neutron star jets not only helps us understand the behavior of these exotic objects, but also sheds light on broader astrophysical phenomena. For example, jets are also produced by black holes and active galactic nuclei, and the mechanisms behind their formation may share similarities with those of neutron star jets. By comparing these systems, scientists can gain deeper insights into the universal principles that govern the most energetic events in the cosmos. As we continue to explore the mysteries of neutron star jets, we uncover new layers of complexity and wonder. These jets are a testament to the incredible forces at play in the universe, reminding us of the dynamic and ever-changing nature of the cosmos. Next, we'll delve into another intriguing aspect of neutron stars, their ages and how scientists determine how old these stellar remnants truly are. Stay tuned as we unravel the mystery of neutron star lifespans. Now, shifting our focus to the passage of time in the cosmos, let's explore the mystery of neutron star ages. Determining how old a neutron star is might seem straightforward, but it's anything but simple. Unlike stars that burn steadily for billions of years, neutron stars are born in the fiery chaos of supernova explosions, and their lifespans are marked by unique and complex processes that make age estimation a fascinating challenge. One of the primary tools scientists use to estimate the age of a neutron star is its rotation rate. When a neutron star is born, it spins incredibly fast, sometimes hundreds of times per second. Over time, however, this rotation slows down due to the emission of energy in the form of radiation and particles. By measuring how quickly a neutron star is spinning today and comparing it to theoretical models of how its rotation should slow over time, scientists can make educated guesses about its age. This method, known as spin-down age estimation, provides a rough timeline but isn't always precise, as other factors like magnetic fields and interactions with surrounding material can influence the star's rotation. Speaking of magnetic fields, they play a crucial role in unraveling the age mystery. Neutron stars are born with extremely strong magnetic fields, but these fields weaken over time. By studying the strength of a neutron star's magnetic field, researchers can gain additional clues about its age. Younger neutron stars tend to have stronger magnetic fields, while older ones have fields that have decayed significantly. However, this method also has its limitations, as the rate of magnetic field decay isn't always consistent and can vary depending on the star's environment and internal structure. Another intriguing aspect of neutron star aging is their cooling process. After their formation, neutron stars are incredibly hot, but they gradually cool down over millions or even billions of years. By measuring the temperature of a neutron star and comparing it to models of how these objects cool, scientists can estimate how long it has been since the star's birth. This method is particularly useful for older neutron stars, as their cooling rates slow down over time, providing a clearer picture of their age. Despite these tools, determining the exact age of a neutron star remains a challenge. Many factors, such as the star's initial conditions, its interactions with other objects, and even the presence of exotic matter in its core, can complicate the calculations. Additionally, neutron stars in binary systems can have their ages skewed by mass transfer from their companions, further muddying the waters. The mystery of neutron star ages isn't just an academic curiosity, it's a window into the life cycle of these extraordinary objects. By piecing together clues from their rotation, magnetic fields, and cooling rates, scientists can better understand how neutron stars evolve and how they fit into the broader tapestry of the universe. As we continue to refine our methods and gather more data, we inch closer to unlocking the secrets of these cosmic timekeepers. Next, we'll dive into another captivating phenomenon: neutron starquakes. These sudden, violent events on the surface of neutron stars reveal even more about their internal structure and the forces at play within them. Stay with us as we explore the seismic activity of these stellar remnants and what it tells us about the universe's most extreme environments. Now, let's turn our attention to one of the most dramatic events in the life of a neutron star: starquakes. These cosmic tremors, often compared to earthquakes but on a much grander scale, offer a fascinating glimpse into the inner workings of these dense stellar remnants. Imagine the surface of a neutron star, a crust of ultra-dense material under unimaginable pressure, suddenly cracking and shifting. This is the essence of a starquake, a phenomenon that releases immense amounts of energy and provides critical clues about what lies beneath the surface. Starquakes occur when the crust of a neutron star, which is incredibly rigid due to the extreme gravitational forces, undergoes sudden stress and fractures. This stress can build up over time as the star's rotation slows down or as its magnetic field evolves. When the pressure becomes too great, the crust cracks, releasing energy in the form of vibrations that ripple through the star. These vibrations can be detected as changes in the star's brightness or as bursts of X-rays and gamma rays, giving scientists a rare opportunity to study the star's interior. One of the most intriguing aspects of starquakes is what they reveal about the internal structure of neutron stars. The way the crust fractures and the energy released during these events provide valuable data about the star's density, composition, and even the state of matter in its core. For instance, the frequency and intensity of the vibrations can help researchers determine how rigid the crust is and how it interacts with the superfluid core beneath it. This information is crucial for understanding the exotic physics at play within neutron stars, where matter is compressed to densities far beyond anything we can replicate on Earth. Another key insight from starquakes is their connection to the star's magnetic field. Neutron stars have some of the strongest magnetic fields in the universe, and these fields can exert tremendous stress on the crust. When a starquake occurs, it can cause a sudden realignment of the magnetic field, leading to a burst of energy known as a magnetar flare. These flares are among the most powerful explosions in the universe, releasing more energy in a fraction of a second than the Sun does in years. By studying these events, scientists can learn more about how magnetic fields evolve and how they influence the behavior of neutron stars. the study of starquakes also sheds light on the broader question of how neutron stars evolve over time. As these stars age, their rotation slows and their magnetic fields weaken, leading to changes in the stress on their crusts. By observing how starquakes become less frequent or less intense as a neutron star ages, researchers can piece together a timeline of its life cycle. This, in turn, helps us understand how neutron stars fit into the larger picture of stellar evolution and the life cycles of stars. Starquakes are more than just cosmic curiosities, they are windows into the extreme physics of neutron stars. Each tremor, each burst of energy, brings us closer to unraveling the mysteries of these enigmatic objects. As we continue to observe and analyze these events, we gain a deeper understanding of the forces that shape the universe and the incredible phenomena that occur within it. Next, we'll explore another captivating aspect of neutron stars, the decay of their magnetic fields. This gradual weakening of their immense magnetic power holds clues to their evolution and the dynamic processes that govern their behavior. Stay tuned as we delve into the fading magnetism of these cosmic giants. Now, let's shift our focus to another fascinating aspect of neutron stars, the gradual decay of their magnetic fields. Over time, these incredibly powerful magnetic fields, which are trillions of times stronger than Earth's, begin to weaken. This process, known as magnetic field decay, plays a crucial role in shaping the life cycle and behavior of neutron stars. The magnetic fields of neutron stars are generated by the motion of charged particles within their interiors. When a neutron star is born from the collapse of a massive star, its magnetic field is at its peak strength. However, as the star ages, the energy driving these magnetic fields starts to dissipate. This happens because the charged particles responsible for generating the field gradually lose their energy, causing the magnetic field to weaken over thousands or even millions of years. One of the key factors influencing this decay is the star's rotation. Neutron stars spin incredibly fast at birth, but over time, their rotation slows down due to the emission of energy in the form of electromagnetic radiation and particles. As the star's spin decreases, so does the dynamo effect that sustains its magnetic field. This slowdown contributes to the gradual weakening of the field, a process that can be observed through changes in the star's emissions and behavior. The decay of a neutron star's magnetic field has significant implications for its evolution. For instance, as the field weakens, the star's ability to emit high-energy radiation, such as X-rays and gamma rays, diminishes. This means that older neutron stars with weaker magnetic fields tend to be less active and less visible in certain wavelengths of light. Over time, they may transition from being highly energetic pulsars or magnetars to quieter, more subdued objects. Another important consequence of magnetic field decay is its impact on the star's crust. The magnetic field exerts immense pressure on the neutron star's surface, and as it weakens, the stress on the crust decreases. This can lead to fewer starquakes and a more stable surface, altering the star's overall behavior. Additionally, the decay of the magnetic field can influence how the neutron star interacts with its surroundings, such as the interstellar medium or any companion stars it may have. Understanding magnetic field decay also helps scientists piece together the life cycle of neutron stars. By studying how these fields weaken over time, researchers can estimate the ages of neutron stars and trace their evolutionary path. This, in turn, provides valuable insights into the broader processes that govern the lives of these cosmic remnants and their role in the universe. The mystery of magnetic field decay is not just about the fading of a star's magnetic power, it's about uncovering the intricate processes that shape the lives of neutron stars. As we continue to study these phenomena, we gain a deeper appreciation for the dynamic and ever-changing nature of the cosmos. Next, we'll explore another intriguing phenomenon, neutron star echoes. These rare and elusive signals offer a unique way to study the environment surrounding these dense stellar objects. Stay with us as we uncover the secrets hidden in these cosmic reverberations. Now, let's turn our attention to a phenomenon that feels almost like a cosmic whisper: neutron star echoes. These rare and elusive signals occur when radiation emitted by a neutron star bounces off nearby material, such as dust or gas, before reaching us. This creates a delayed echo, a kind of cosmic reverberation that offers a unique window into the environment surrounding these dense stellar objects. Imagine a flashlight shining in a dark room. If the light hits a mirror, it bounces back, creating a reflection. Neutron star echoes work in a similar way. When a neutron star emits radiation, whether it's X-rays, gamma rays, or radio waves, some of that energy can interact with surrounding material. Instead of traveling directly to us, the radiation scatters off this material, creating a delayed signal that arrives slightly later than the original emission. These echoes are faint and often difficult to detect, but when observed, they provide valuable clues about the structure and composition of the space around the neutron star. One of the most intriguing aspects of neutron star echoes is what they reveal about the interstellar medium, the gas and dust that fill the space between stars. By studying the timing and intensity of these echoes, scientists can map out the distribution of this material and even estimate its density. This is particularly useful for understanding regions of space that are otherwise difficult to observe directly. For example, echoes can help us identify clouds of gas or dust that might be too diffuse or distant to detect through other means. Another fascinating application of neutron star echoes is their ability to shed light on the history of the neutron star itself. The echoes can carry information about past outbursts or flares from the star, acting like a cosmic recording of its activity. By analyzing these delayed signals, researchers can piece together a timeline of the star's behavior, revealing patterns or changes that might otherwise go unnoticed. This makes echoes a powerful tool for studying the long-term evolution of neutron stars and their interactions with their surroundings. Detecting neutron star echoes is no easy task. The signals are often faint and can be easily drowned out by other sources of radiation. However, advances in technology, such as more sensitive telescopes and sophisticated data analysis techniques, are making it increasingly possible to identify and study these elusive phenomena. Each new detection adds another piece to the puzzle, helping us better understand the complex environments around neutron stars. The mystery of neutron star echoes is a reminder of how much we still have to learn about the universe. These faint, delayed signals carry stories of cosmic interactions, hidden structures, and the dynamic lives of neutron stars. As we continue to explore these echoes, we uncover not just the secrets of neutron stars, but also the intricate web of matter and energy that connects them to the wider cosmos. Next, we'll delve into another captivating mystery: the faint halos of radiation that sometimes surround neutron stars. These glowing envelopes hold clues about the star's environment and history, offering yet another layer of insight into these enigmatic objects. Stay with us as we explore the secrets of neutron star halos. Now, let's shift our focus to another fascinating phenomenon: the mysterious halos of radiation that occasionally envelop neutron stars. These faint, glowing envelopes are more than just a cosmic spectacle. They hold vital clues about the environment and history of these dense stellar remnants. Picture a neutron star as a lighthouse, but instead of just beams of light, it's surrounded by a shimmering aura that tells a story of its past and present. These halos are created when the intense radiation emitted by the neutron star interacts with the surrounding interstellar medium. As the star's radiation travels outward, it can collide with particles of gas and dust, causing them to glow. This process, known as scattering, produces a faint halo that can extend far beyond the star itself. While these halos are often too dim to see directly, advanced telescopes and imaging techniques have allowed scientists to detect and study them in greater detail. One of the key insights these halos provide is about the density and composition of the material surrounding the neutron star. By analyzing the brightness and structure of the halo, researchers can estimate how much gas and dust are present in the star's vicinity. This information is crucial for understanding the star's environment, as it reveals whether the neutron star is moving through a dense cloud of interstellar material or a relatively empty region of space. In some cases, the halo can even indicate the presence of previously undetected structures, such as remnants of a supernova explosion that created the neutron star. Another intriguing aspect of neutron star halos is their ability to act as a historical record. The radiation that forms the halo can carry traces of the star's past activity, such as powerful flares or outbursts. By studying the halo's properties, scientists can piece together a timeline of the star's behavior, uncovering patterns or changes that might otherwise remain hidden. This makes halos a valuable tool for understanding the long-term evolution of neutron stars and their interactions with their surroundings. Detecting and studying these halos is no small feat. They are often faint and can be easily overshadowed by the brightness of the neutron star itself or other sources of radiation in the sky. However, advancements in observational technology, such as more sensitive telescopes and sophisticated data analysis methods, are making it increasingly possible to uncover these elusive features. Each new discovery adds to our understanding of neutron stars and the complex environments they inhabit. The mystery of neutron star halos reminds us of the intricate connections between these stellar objects and the space around them. These faint glows are not just beautiful cosmic phenomena. They are windows into the past and present of neutron stars, offering insights into their formation, evolution, and interactions with the interstellar medium. As we continue to explore these halos, we uncover more about the dynamic and ever-changing nature of the universe. Next, we'll dive into another captivating mystery: the high-speed winds of particles that some neutron stars emit. These powerful outflows shape the space around them and reveal even more about the extraordinary behavior of these cosmic objects. Stay tuned as we explore the secrets of neutron star winds. Now, let's turn our attention to another extraordinary feature of neutron stars: their high-speed winds. These aren't the gentle breezes you might feel on Earth. These are powerful streams of particles racing outward at incredible speeds, shaping the space around them in dramatic ways. Imagine a cosmic storm where the neutron star acts as the engine, blasting particles into the void with enough force to influence its surroundings on a massive scale. These winds are made up of charged particles such as electrons and protons, accelerated by the neutron star's intense magnetic fields and rapid rotation. As these particles are ejected, they travel at speeds close to the speed of light, creating a dynamic and energetic environment around the star. This process is particularly common in pulsars, where the combination of strong magnetic fields and fast rotation generates these powerful outflows. One of the most fascinating aspects of neutron star winds is how they interact with the interstellar medium, the gas and dust that fill the space between stars. As the wind collides with this material, it can create shock waves, heating the surrounding gas and causing it to glow. These interactions often result in spectacular structures such as nebulae, which can be observed by telescopes. In some cases, the wind's energy is so immense that it carves out vast cavities in the interstellar medium, leaving behind a trail of ionized gas and radiation. The impact of these winds isn't just visual, it also has significant implications for the star's environment. By pushing against the interstellar medium, the wind can slow down the neutron star's motion over time. This process, known as braking, affects the star's rotation and magnetic field, providing clues about its evolution. Additionally, the wind can enrich the surrounding space with heavy elements, contributing to the chemical makeup of the galaxy. Studying neutron star winds is no easy task. Their high speeds and the vast distances involved make direct observation challenging. However, scientists use a combination of X-ray and radio observations to detect the effects of these winds. By analyzing the radiation emitted during the wind's interactions with the interstellar medium, researchers can piece together the properties of the wind, such as its speed, density, and energy. These observations help us understand not only the winds themselves, but also the broader role they play in shaping the cosmos. The mystery of neutron star winds highlights the dynamic and interconnected nature of the universe. These powerful outflows are more than just a byproduct of a neutron star's activity. They are a key part of its story, influencing its surroundings and leaving a lasting mark on the galaxy. As we continue to study these winds, we uncover more about the incredible forces at work in the universe and the ways in which even the smallest objects can have a profound impact. Next, we'll explore another intriguing aspect of neutron stars, the possibility of superfluid interiors. What happens when matter flows without friction inside these dense stellar remnants? Stay with us as we dive into the strange and fascinating world of neutron star superfluids. Now, let's venture into one of the most mind-bending mysteries of neutron stars, the possibility of superfluid interiors. Picture this: deep within the core of a neutron star, matter behaves in ways that defy everything we know about physics on Earth. Here, the rules of friction don't apply and particles flow freely, as if they've unlocked the secrets of perpetual motion. This strange state of matter is known as a superfluid, and it's one of the most fascinating aspects of neutron star science. Superfluidity occurs when matter, typically a liquid, flows without any resistance. On Earth, we've observed this phenomenon in extremely cold environments, like liquid helium cooled to near absolute zero. But inside a neutron star, the conditions are even more extreme. The immense pressure and density create an environment where neutrons, the building blocks of the star, can form a superfluid. This means that in the core of a neutron star, matter can move without losing energy, creating a frictionless flow that's almost impossible to imagine. So, how does this superfluid interior affect the neutron star? One of the most significant impacts is on the star's rotation. Neutron stars are known for their incredibly fast spins, with some rotating hundreds of times per second. The superfluid core plays a crucial role in this. As the outer layers of the star slow down due to interactions with the surrounding environment, the superfluid core can continue spinning at a different rate. This mismatch between the core and the crust can lead to sudden changes in the star's rotation, a phenomenon known as a glitch. These glitches provide scientists with valuable clues about the internal structure of neutron stars and the behavior of superfluids under such extreme conditions. But the influence of superfluidity doesn't stop there. It also has a profound effect on the neutron star's magnetic fields. The frictionless flow of the superfluid can generate powerful currents, which in turn can amplify or alter the star's magnetic field. This interaction between the superfluid and the magnetic field is still not fully understood, but it's believed to play a key role in shaping the star's observable properties, such as its X-ray emissions and pulsar activity. Studying neutron star superfluids is no easy task. The extreme conditions inside these stars make direct observation impossible, so scientists rely on theoretical models and indirect evidence, such as glitches and changes in rotation rates, to piece together the puzzle. By combining these observations with advanced simulations, researchers are slowly unraveling the mysteries of superfluid interiors and their impact on neutron star behavior. The existence of superfluids in neutron stars challenges our understanding of matter and opens up new questions about the fundamental laws of physics. What other strange states of matter might exist in the universe? How do these states influence the evolution of stars and galaxies? As we continue to explore these questions, neutron stars remain one of the most exciting laboratories for testing the limits of our knowledge. Next, we'll take a closer look at the enigmatic cores of neutron stars, where matter may exist in even more exotic forms. What lies at the very heart of these cosmic powerhouses? Stay with us as we uncover the secrets of neutron star cores. Now, let's dive deeper into the heart of neutron stars, where the mysteries only grow more profound. At the very core of these cosmic powerhouses, matter exists in states so extreme that they challenge our understanding of physics itself. Here, the pressures are unimaginable, so intense that the very building blocks of matter may break down into something entirely different. Scientists believe that neutron star cores could be home to exotic forms of matter, such as quark-gluon plasma or even strange matter. Quark-gluon plasma is a state of matter where protons and neutrons dissolve into their fundamental components, quarks and gluons. This state is thought to have existed just moments after the Big Bang, when the universe was a seething, hot soup of particles. Inside a neutron star's core, the crushing pressure might recreate these conditions, allowing quarks to roam freely rather than being confined within protons and neutrons. This would mean that the core of a neutron star could be a window into the earliest moments of the universe, offering clues about how matter first formed. But that's not all. Some theories suggest that neutron star cores might contain something even stranger, literally. Strange matter is a hypothetical form of matter made up of quarks, including the elusive strange quark. Unlike ordinary matter, strange matter could be more stable under the extreme conditions found in neutron star cores. If this is true, it could mean that the core of a neutron star is a completely different kind of substance, one that doesn't exist anywhere else in the universe. The implications of these exotic states are staggering. If neutron star cores do contain quark-gluon plasma or strange matter, it would fundamentally change our understanding of how matter behaves under extreme conditions. It could also provide insights into the nature of the strong nuclear force, one of the fundamental forces that hold atoms together. But studying these cores is no easy feat. The conditions inside a neutron star are so extreme that they can't be replicated in any laboratory on Earth. Instead, scientists rely on observations of neutron star behavior, such as their rotation rates and gravitational wave emissions, to infer what might be happening deep within their cores. As we continue to explore these enigmatic cores, one thing is clear. Neutron stars are not just remnants of supernova explosions. They are cosmic laboratories offering us a glimpse into the most extreme states of matter in the universe. What other secrets might they hold? As we move forward, we'll explore the final mystery of neutron stars, their ultimate fate. What happens when these incredible objects reach the end of their lives? Stay with us as we uncover the answers. Now, shifting our focus to another fascinating aspect of neutron stars, let's explore the mystery of their magnetic field alignment. Neutron stars are known for their incredibly strong magnetic fields, but what's even more intriguing is how these fields align and what that means for the star's behavior and the signals we detect from them. Magnetic fields in neutron stars are not always uniform or straightforward. In some cases, the magnetic axis, the direction of the magnetic field, doesn't align with the star's rotational axis. This misalignment creates a unique phenomenon where the magnetic poles sweep through space as the star rotates, much like a lighthouse beam. This is what gives rise to pulsars, the rapidly spinning neutron stars that emit beams of radiation we detect as pulses. But why does this misalignment occur? One theory suggests that during the formation of a neutron star, the magnetic field can become tilted due to the chaotic conditions of a supernova explosion. As the star collapses, the magnetic field lines may not settle into a perfectly aligned state, leading to this offset. Over time, the magnetic field might gradually realign with the rotational axis, but this process could take millions of years, leaving us with neutron stars in various stages of alignment. The alignment or misalignment of a neutron star's magnetic field has significant effects on its observable properties. For instance, the angle between the magnetic and rotational axes determines how bright the pulsar appears from Earth. If the beams of radiation sweep directly across our line of sight, we see a bright, regular pulse. If they don't, the pulsar might appear dimmer or even invisible to us. This variability makes studying neutron stars both challenging and rewarding, as it provides clues about their internal structure and the forces shaping their magnetic fields. Interestingly, some neutron stars exhibit what's known as magnetic field decay, where the strength of the magnetic field weakens over time. This decay can also influence the alignment, potentially causing the magnetic axis to shift closer to the rotational axis. Observations of this process help scientists understand how neutron stars evolve and how their magnetic fields interact with their surroundings. The study of magnetic field alignment in neutron stars isn't just about understanding these cosmic objects, it's also about unraveling the fundamental physics of magnetism in extreme environments. By observing how these fields behave, we gain insights into the nature of matter, energy, and the forces that govern the universe. As we continue to probe the mysteries of neutron stars, the alignment of their magnetic fields remains a key piece of the puzzle. What other secrets might this alignment reveal, and how might it shape our understanding of the cosmos? These questions drive scientists to keep exploring, pushing the boundaries of what we know about these extraordinary objects. Next, we'll turn our attention to the final mystery, the ultimate fate of neutron stars. What happens when these cosmic powerhouses reach the end of their lives? Stay with us as we uncover the answers. Now, as we approach the final chapter in the life of a neutron star, let's explore the mystery of their ultimate fate. Neutron stars, despite their incredible density and strength, are not immortal. Like all cosmic objects, they too face an end, but what that end looks like is one of the most intriguing questions in astrophysics. One possible fate for a neutron star is a dramatic collapse into a black hole. This can happen if the neutron star gains too much mass, either by pulling in material from a companion star or through a collision with another neutron star. When the star's mass exceeds a critical limit, known as the Tolman-Oppenheimer-Volkoff limit, the immense gravitational force overwhelms the pressure exerted by neutrons, causing the star to collapse. This sudden collapse triggers the formation of a black hole, a region of space where gravity is so intense that not even light can escape. Such events are not only spectacular, but also provide valuable insights into the nature of gravity and spacetime. But not all neutron stars meet such a dramatic end. Some may simply fade away over billions of years. As a neutron star ages, it loses energy through radiation and the emission of particles, gradually cooling down. Over time, its magnetic field weakens and its rotation slows. Eventually, it may become a cold, dark remnant, barely detectable in the vastness of space. These dead neutron stars, sometimes called black dwarfs if they cool completely, represent the quiet end of a once vibrant cosmic powerhouse. There's also the possibility that neutron stars could transform into something even more exotic. Some theories suggest that under extreme conditions, the matter in a neutron star's core could undergo a phase transition, turning into strange matter, a hypothetical form of matter made up of strange quarks. If this happens, the entire star could be converted into a strange star, an object with properties even more bizarre than those of a neutron star. While this remains speculative, it opens up fascinating possibilities for what might lie at the heart of these enigmatic objects. The death of a neutron star isn't just a cosmic curiosity, it's a key piece of the puzzle in understanding the life cycle of stars and the evolution of the universe. By studying how neutron stars end their lives, scientists can learn more about the fundamental forces that shape the cosmos, from gravity to the behavior of matter under extreme conditions. As we wrap up our exploration of neutron stars, we're left with a profound sense of awe at the complexity and beauty of these celestial objects. From their birth in the fiery aftermath of supernova to their mysterious deaths, neutron stars continue to challenge our understanding of the universe. What other secrets might they hold, and how will future discoveries reshape our knowledge of these cosmic wonders? The answers lie in the stars themselves, waiting to be uncovered by the next generation of explorers. Now, let's step back and consider the bigger picture, the role neutron stars play in the grand tapestry of the cosmos. These extraordinary objects are more than just remnants of stellar explosions. They are key players in shaping the universe as we know it. One of their most significant contributions lies in galactic evolution. When neutron stars collide or merge, they release immense amounts of energy and heavy elements like gold, platinum, and uranium into space. These elements, forged in the heart of these cosmic collisions, eventually become part of new stars, planets, and even life itself. Without neutron stars, the universe as we know it would lack many of the building blocks essential for complexity and diversity. But neutron stars are not just cosmic forges, they are also unparalleled laboratories for testing the laws of physics. Their extreme conditions, from their crushing densities to their unimaginable magnetic fields, allow scientists to explore phenomena that cannot be replicated on Earth. For instance, the behavior of matter under such intense pressure provides clues about the nature of nuclear forces and the possible existence of exotic states of matter like quark-gluon plasma. Neutron stars also serve as natural testbeds for Einstein's theory of general relativity. The gravitational waves produced by their collisions offer a unique window into the fabric of spacetime, helping us refine our understanding of gravity itself. Beyond their scientific value, neutron stars also influence the structure and dynamics of galaxies. Their powerful magnetic fields and high-energy emissions can shape the surrounding interstellar medium, triggering star formation or clearing out regions of space. Some neutron stars, particularly those with strong jets, act as cosmic particle accelerators, sending streams of high-energy particles across vast distances. These interactions contribute to the intricate balance of forces that govern the life cycles of galaxies. In essence, neutron stars are not just relics of the past, they are active participants in the ongoing story of the universe. They challenge our understanding of physics, enrich the cosmos with heavy elements, and shape the environments around them. As we continue to study these enigmatic objects, we uncover not only their secrets but also deeper truths about the universe itself. The next time you look up at the night sky, remember that somewhere out there, neutron stars are quietly shaping the cosmos, one collision, one burst, and one mystery at a time. As we look ahead, the future of neutron star research is brimming with exciting possibilities. New missions and cutting-edge technologies are set to revolutionize our understanding of these enigmatic objects. One of the most anticipated advancements is the development of next-generation telescopes, like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope. These instruments will allow us to peer deeper into the cosmos with unprecedented clarity, capturing detailed images and spectra of neutron stars and their surroundings. By studying their light across different wavelengths, we can uncover clues about their composition, magnetic fields, and interactions with their environments. Another groundbreaking area of research lies in gravitational wave astronomy. Following the success of observatories like LIGO and Virgo, new detectors such as the Einstein Telescope and the Laser Interferometer Space Antenna, or LISA, are on the horizon. These advanced instruments will be sensitive enough to detect even fainter gravitational waves from neutron star mergers and other cosmic events. This will provide us with a richer dataset to explore the internal structure of neutron stars, test theories of gravity, and potentially discover new phenomena that challenge our current understanding of physics. In addition to telescopes and gravitational wave detectors, advancements in computational modeling are set to play a crucial role. Supercomputers are becoming increasingly powerful, enabling scientists to simulate the extreme conditions within neutron stars with greater accuracy. These simulations can help us predict how neutron stars behave under different scenarios, from their formation in supernova to their collisions and eventual fates. By combining these models with observational data, researchers can refine their theories and uncover new insights into the nature of matter and energy in the universe. Collaborative international efforts are also driving progress in neutron star research. Projects like the Square Kilometre Array, or SCAR, aim to create the world's largest radio telescope network, offering unparalleled sensitivity to study pulsars and other neutron star phenomena. These global initiatives not only bring together the brightest minds in astrophysics, but also foster innovation in technology and data analysis, pushing the boundaries of what we can achieve. As we stand on the brink of these technological breakthroughs, the mysteries of neutron stars are closer than ever to being unraveled. Each new discovery brings us one step closer to understanding the fundamental forces that shape our universe. And with every mission, telescope, and detector, we are reminded that the cosmos still holds countless secrets waiting to be uncovered. The journey to decode the strange behavior of neutron stars is far from over, and the future promises to be as thrilling as the discoveries we've made so far. Now, let's shift our gaze from the scientific to the cultural and explore how neutron stars have left their mark not just on the cosmos, but on our collective imagination. These enigmatic objects, with their extreme density and bizarre behavior, have become a source of fascination far beyond the realm of astrophysics. They've inspired artists, writers, and filmmakers, weaving their way into the fabric of science fiction and popular culture. In science fiction, neutron stars often serve as the backdrop for stories that push the boundaries of human imagination. Their intense gravitational fields and exotic environments make them the perfect setting for tales of survival, exploration, and discovery. For instance, in Larry Niven's classic novel Neutron Star, the protagonist navigates the deadly tidal forces near one of these stars, showcasing the awe-inspiring and terrifying nature of these cosmic objects. Similarly, in the Star Trek universe, neutron stars have been featured as navigational hazards and sources of scientific intrigue, highlighting their role as both a challenge and a wonder. But it's not just in literature and television where neutron stars shine. They've also inspired visual artists and musicians who use their mysterious qualities to evoke a sense of the sublime. The pulsating beams of radiation from pulsars, for example, have been likened to cosmic lighthouses, guiding humanity's imagination through the vastness of space. This imagery has found its way into album covers, digital art, and even orchestral compositions, where the rhythmic pulses of neutron stars are mirrored in the beats and melodies of music. Beyond art and entertainment, neutron stars have also captured the public's curiosity, becoming a symbol of the unknown and the extraordinary. Their discovery and study have sparked countless discussions about the nature of the universe, our place within it, and the limits of human knowledge. Public lectures, documentaries, and even social media campaigns have brought the mysteries of neutron stars to a wider audience, making them a gateway for people to engage with the wonders of astrophysics. In many ways, neutron stars are more than just celestial objects, they are cultural icons. They remind us of the beauty and complexity of the universe, and they challenge us to think beyond the confines of our everyday lives. Whether through the lens of science, art, or storytelling, neutron stars continue to inspire us to dream, explore, and question the cosmos. And as we uncover more about their secrets, their cultural impact will only grow, bridging the gap between the scientific and the imaginative, and reminding us that the universe is as much a source of wonder as it is of knowledge. As we bring our journey through the mysteries of neutron stars to a close, it's clear that these cosmic wonders are far more than just dense remnants of stellar explosions. From their formation in the fiery aftermath of supernovas to their role as cosmic laboratories for testing the limits of physics, neutron stars challenge our understanding of the universe in profound ways. We've explored their rapid spins, their powerful magnetic fields, their enigmatic interiors, and even their ability to create heavy elements like gold and platinum. Each mystery we've uncovered, whether it's the strange behavior of pulsars, the explosive power of magnetars, or the gravitational waves produced by their collisions, reveals just how much we still have to learn about these extraordinary objects. Neutron stars are not just scientific curiosities, they are windows into the extreme conditions that shape our universe. They remind us that the cosmos is filled with phenomena that defy our everyday experiences, pushing the boundaries of what we thought was possible. By studying them, we gain insights into the fundamental forces of nature, the origins of the elements, and the very fabric of space and time. They are, in many ways, the ultimate cosmic puzzles waiting to be solved. But the story of neutron stars doesn't end here. With every new discovery, we uncover more questions, more mysteries to explore. And that's the beauty of science. It's a never-ending journey of curiosity and wonder. So, as we wrap up this exploration, I encourage you to keep looking up, to keep asking questions, and to keep marveling at the incredible universe we live in. If you've enjoyed this deep dive into the strange and fascinating world of neutron stars, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss out on our cosmic adventures. And of course, share your thoughts in the comments below. What mystery of neutron stars fascinates you the most? Let's keep the conversation going, because the universe is full of wonders and together we can uncover them. Thanks for watching, and until next time, keep exploring.